Today we will say some more about Laplace transforms. Recall that the Laplace transform of f of t is given by the integral from 0 to infinity of f of t e to the minus st dt, and we notate that as capital F of s. So standard notation here, Laplace transform of little f of t is capital F of s. And we've calculated some of these things, and this is what we know so far. Laplace transform of 1 is 1 over s. Laplace transform of e to the at is 1 over s minus a. ua of t, which you'll remember is the unit step function, it's 0 when t is less than a, and it's 1 after that. The transform is e to the minus sa over s. Laplace transform of t is 1 over s squared, and Laplace transform is linear. The transform of af of t plus bg of t is a transform of f plus b transform of g. Now, let's take a look at the transform of t, which we calculated last time, and we used integration by parts because the integrand looked like that was the right thing to do. Now, we could actually have done a more general problem, not just t, but t to the n, where n is a positive integer. So let's take a look at that. The process is going to work exactly the way it did before. Laplace transform of t to the n is this integral, which is the standard limit as k goes to infinity of this integral. And now we're looking at this integrand. The way to do this is by parts. We're going to have u be t to the n, which means du is going to be n t to the n minus 1 dt. dv is what's left, which is e to the minus st dt. Take an antiderivative and you get minus e to the minus st over s. So this integral from 0 to k is actually then uv evaluated between 0 and k minus the integral of v du. And when we look at this quantity, at 0 we get 0, and at k we get k to the n e to the minus sk over s. And as k goes to infinity, that term goes to 0 as long as s is positive, because this exponential overpowers the polynomial. And that means this term dies off, and we obtain this integral is equal to just this piece. And what we recognize here is this is the Laplace transform of t to the n, and this is the Laplace transform of t to the n minus 1 multiplied by n over s. And that gives us this formula that the Laplace transform of t to the n is n over s, Laplace transform of t to the n minus 1. Now we can just use that to bootstrap. We know the Laplace transform of t is 1 over s squared, so the Laplace transform of t squared is going to be 2 over s, Laplace transform of t, which is known to be 1 over s squared, so we get 2 over s cubed. Same thing with t cubed. 3 over s times this transform, which gives us 3 times 2 over s to the 4th. And as we continue along, what we get on the top is just n times n minus 1 all the way down to 2 over s to the n plus 1, which we recognize as n factorial over s to the n plus 1. Okay, so we have another thing for the table, which is the transform of t to the n when n is a positive integer. Now what we're going to do is we're going to look at the Laplace transform of the cosine of bt, which is the integral from 0 to infinity cosine bt e to the minus st dt. Now, on first viewing, this looks to be a really computationally complex problem. Many of you will recognize this integral, cosine x times e to the x dx, is an integral that was done by parts in second semester calculus. lots of times is the culmination of look at all the integrals we can do. And he ended up integrating by parts twice, setting up an equation for the integral, and then solving for it algebraically. So it was probably the most complicated problem you ever did by parts. Okay? But we actually can compute this in a much faster way, and in the process, we'll get the Laplace transform of the sine of bt along with it. And the trick is our complex number formula, Euler's formula. Recall that e to the I bt is cosine bt plus I sine bt, which means that the Laplace transform of e to the I bt will be the Laplace transform of cosine bt plus I sine bt. And now because of linearity, that's the Laplace transform of the cosine of bt plus I times the Laplace transform of the sine of bt, which means the Laplace transform of this thing is going to be a complex function. The real part is going to be the Laplace transform of cosine bt, and the imaginary part is going to be the Laplace transform of the sine of bt. Now, before we go ahead and actually write down an integral, we realize we don't even have to do that, because we know what the Laplace transform of e to the at is. It's 1 over s minus a. So we just insert ib every place that we see an a here, and we have the Laplace transform of e to the ibt is 1 over s minus ib. Now, all we really have to do is take s minus ib and put it in a more convenient form. We multiply top and bottom by the complex conjugate. On the top, we get s plus ib, and on the bottom, we get s squared minus I squared b squared, which is plus b squared. So you've got s plus ib over s squared plus b squared. And we split that up into the real part, which is s over s squared plus b squared, plus I times the imaginary part, which is b over s squared plus b squared. And according to what we've seen here, the Laplace transform of the cosine of bt, the real part, is this, and the Laplace transform of the sine of the bt is the imaginary part, which is this. So we know Laplace transform of the cosine, and we know the Laplace transform of the sine. Okay, and I didn't make a big deal of this, but both of these turn out to be true when s is bigger than 0. Okay, now we come to maybe the most important of the Laplace transformations as far as we're concerned, because this is, of course, a differential equation. What do derivatives transform like? Okay, so we're going to transform f prime of t, and we're going to assume that both f of t and f prime of t have Laplace transforms. Okay, so if the Laplace transform of little f is capital F of s, what is the Laplace transform of its derivative? So the Laplace transform of f prime of t is equal to the integral from 0 to infinity of f prime of t e to the minus st dt, which is the lim as k goes to infinity of the integral from 0 to k of f prime of t e to the minus st dt. Now, this last integral, we're going to do by parts again. We choose u equals e to the minus st, and dv, f prime of t dt. The idea being here, we want to integrate f prime of t to get to f of t, which we know something about the transform of. So v is f of t, du is minus s e to the minus st dt. So our integral becomes uv, which is f prime of t e to the minus st, minus v f of t du, which is minus s e to the minus st dt. And that means that when we take the limit of this integral, it's the same as taking the limit as case goes to infinity of this integral. You evaluate this thing at 0, you get f of 0. You evaluate this thing at k, you get f of k e to the minus sk. And remember that f is exponentially bounded because it has a Laplace transform, which means this limit is going to go to 0 for some real s. And that means that all we're left with is this minus f of 0. And now this thing we recognize as s times the Laplace transform of f of t. So what we have just discovered is that the Laplace transform of f prime is minus f of 0 plus s times the Laplace transform of the derivative of f. And now this is what's important. A derivative in t turns into multiplication in s. And that's the reason this is worth a lot, because you can transform differential equations in t into algebraic equations in s. Okay, so a review. Here's our current table. This is one of the things we did today, the Laplace transform of t to the n. We did cosine and sine. This is well known from the last time, and this is the important one that we just did. The transform of f prime is minus f of 0 plus s times the transform of f. So as an example of this last thing, let's suppose we have some function little f, and we know that f of 0 is 1. And we know that its Laplace transform is s over s squared minus 4. What is the Laplace transform of the derivative? And the answer is it's minus f of 0 plus s cap f of s, and that's going to be minus 1 because f of 0 was 1, s times the Laplace transform, which we knew was s over s minus 4. We do a little algebra here. There's an s squared here. This minus 1 has to get put into here as s squared minus 4 over s squared minus 4. You do the algebra, you get 4 over s squared minus 4. So if we know the Laplace transform of the function, and we know something about the value of the function 0, we can find the Laplace transform of the derivative. Okay, now, if you remember, the process that we were talking about was take a problem, and in the example I said in French, and that's T language, translate it into English, which is S language, solve it in English, which is S language, and then translate it back to French, which is T language. Now, our translation software to get from T to S is the Laplace transform. We're going to do some sort of a solution over here, but we need to get back. And that's going to be the inverse Laplace transform. And for there to be an inverse Laplace transform, L is going to have to be a one-to-one function, okay? Because we can't have two different functions having the same Laplace transform, because if you tried to go back, which of them do you go back to? Okay, so Laplace transform of f equaling Laplace transform of g must mean that f is g, and that turns out to be true, except for minor issues involving discontinuities. And we'll deal with those later, but except for that, L is one-to-one, and L inverse does exist. And because L is linear, L inverse is going to turn out to be linear too. And now if you want to look at why that's true, we know the Laplace transform of AF of t plus BG of t is AF of s plus BG of s. We saw that last time. So if you take L inverse of both sides, L inverse of L is just going to be AF plus BG. L inverse of this is whatever it is. And now the thing is that f of t is the inverse of cap f of s, because L takes little f of t to cap f of s, so L inverse takes you back. Okay, g of t is the inverse transform of cap g of s. So if you look here, this is A, inverse transform of cap f. This is B, inverse transform of cap g, and that's equal to inverse transform AF of s plus B g of s, and that's exactly what it means to be linear. So we can use the standard things that we've used always. You take transforms of various things, and you multiply them by stuff, and you add them together, and you've still got transforms. Okay, now, here's the nice thing. We don't need a formula for the inverse transform, because we've got a table that shows us how to get from t to s. If we read the table backwards, it's going to tell us how to get from s to t. So as an example, let's inverse transform 3 over s plus 2 over s minus 5. So in other words, we're in s space, we want to get back to t space. Well, the first thing to recognize here is that 1 over s is the Laplace transform of 1, and 1 over s minus 5 is the Laplace transform of e to the 5t. We can see that from the table. So the inverse transform of 1 over s is 1. The inverse transform of 1 over s minus 5 is e to the 5t. So to inverse transform this more complicated expression, we use the linearity. And we're going to get here 3 times the inverse transform of 1 over s plus 2 times the inverse transform of 1 over s minus 5. And now that's just 3 times 1 plus 2 times e to the 5t. Second example, let's find the inverse transform of f of s equals s plus 6 over s squared plus 9. Now, if you end up looking in the table, you're going to see things that look like s squared plus b squared, and those are sines and cosines. And in fact, the Laplace transform of the cosine of bt is s over s squared plus b squared, and the Laplace transform of sine bt is b over s squared plus b squared. So the Laplace transform of cosine of 3t is the s over s squared plus 9, and the transform of the sine of 3t is 3 over s squared plus 9. Now this 3 is going to be important, because when we take s plus 6 over s squared plus 9, we want to break it up as s over s squared plus 9. And now 3 over s squared plus 9, but we got a 6 here, so it's 3 times 2. So it's one of these and 2 of those is how to get this thing. So when we inverse transform, we get one of those and 2 of those. So the inverse transform of s plus 6 over s squared plus 9 is cosine 3t plus 2 sine